Welcome to the morning plenary talk. It's a real pleasure to introduce the next speaker, a friend of mine, a collaborator. Piotr, at the age of 40, has written already 100 papers, cited 500 times. But even more importantly, Piotr is very much involved in mathematical community in Poland, and he's very active not only in administration. He's the dean of science in Krakow, but also he served on various committees in Warsaw, helping to communicate the specific needs that our community have of mathematicians in Poland to the government, and well, he helped to explain what is it that we need to do good mathematics, and he helped to communicate how our work should be evaluated. Please welcome Piotr Oprocha.
Thank you very much. And first of all, let me thank the organizers, because without their help, I would be not here today, because my flight was cancelled and I was locked in Toronto, but then somehow I managed via communication with Tom to rearrange my shuttle and finally come here, so thank you very much. Okay, so this talk will be combination of survey on minimal systems, and then I will present some joint works with Jan, who introduced me, and with Alex, who is now in Leicester, UK. And this talk is dedicated to memory of Sergei Kolyada, who unfortunately passed away May this year. He made lots of contribution in topological dynamics, and probably from his paper, I learned the first time about transitivity and other notions in topological dynamics. So we will really miss him as a person and in mathematics. Okay, so I know that maybe not everybody here is working in dynamics. So the first part will be quite kind of introduction. So if I'm repeating well-known things, so forgive me for that, but I hope it will be helpful. Okay, so for me, dynamical system, it will be pair consisting of compact metric space, so I always have metric, and continuous map, and in many cases, it will be homeomorphism. And in theory of dynamical system, the first papers were about homeomorphism, and then people start to look at onto maps or even only continuous, and then there are some problems with terminology, and I will also speak about it a little later. Okay, so main object for the whole talk are minimal sets. So I have my map, I'm iterating this map, and then if I can find non-empty set which is invariant, so my map don't go outside of this set, and there is no other closed invariant non-empty set, then I call my set minimal, and it is the smallest dynamical object in your map that you can observe. You cannot decompose it anymore from point of view of dynamics. So it is why these sets are important. And there are many different conditions how to obtain these minimal sets or how to construct them. I will show you some techniques later. But this is one of well-known characterizations. So other way of saying that set is minimal is saying that every point has dense orbit in this set. So any point you choose in your M and you iterate, it will generate dense subset. Okay, and sometimes I will speak about minimal space, and by minimal space, not set. It is why I will distinguish between set and space. So minimal space for me is compact metric set where I can find some minimal map on it, map for which the whole space is minimal. Okay, and also factor between systems. I will be using this quite often in this talk. So factor means if I have two dynamical systems, then I have surjective map from this space to that space, such that it commutes with the dynamics. Okay, so usually here you will have richer dynamics than there, but still you want to have, in some sense, similar dynamics. Okay, so when you start to think about examples, then standard ones are rotations, so you can have rotation of the circle. For rotation, irrational rotation on the circle, every orbit is dense, so from this equivalent definition you see that the space, that circle is example of minimal space. Of course, you can have periodic orbit, that's the easiest minimal set, just finite set with permutation of all points. So these are classical. Other classical examples are odometers or adding machine, depending who define them. So here the dynamics is very similar to periodic orbit. So you have finite sets, and then you construct inverse limit, and you add on each coordinate by 1. Okay, so maybe on the first level you have 2 points and you just go cyclically. Next level you have 4 points and you go around, but you also have this banding map which keeps that you don't change levels in some sense. Okay, so this is also classical generalization. In fact, both of those are classical generalizations of what you see for periodic orbit. If you have periodic orbit, then irrational rotation on the circle is one possibility, and these adding machines, they are other possibilities, which are in some sense similar to periodic orbit. Okay, but of course there are many others, and here is one possibility, which is so-called two-mode system. So you have substitution, you substitute 0 by 0, 1, 1 by 1, 0, and you start with 0 and start these substitutions, and then you generate infinite sequence. Okay, so like 0 goes to 0, 1, 0, 1 goes to 0, 1, and 1 goes to 1, 0, and so on. That way you build this. And this is also technique, kind of standard techniques to build minimal systems. So you just fix this substitution, and in each word you keep 2 symbols, and you do it. And then you take this sequence, you take shift map, so take all possible shifts, and you take closure of this in full shift. And that way you obtain minimal system. Okay, so this is, you are now in space of 0, 1 sequences. It is not immediately seen that if you do it, it's minimal system, but there is whole theory saying that you can do that. And this is one of the classics. So if you look for minimal systems, then probably you will find one of those at some point. Okay. So also when you work in topological dynamics, then you are interested in different degrees of mixing and what mixing means in your map. And here, so transitivity means that eventually one open set intersects other one. So in minimal system, you always have this transitivity, okay, because every point has dense orbit. So starting in n open set, you will eventually enter another one. So transitivity is always in minimal systems. But then you have the stronger property of weak mixing, which means that if you take product of your system with itself, it's transitive. And this is kind of equivalent condition to look at weak mixing. So weak mixing means that if I fix 2 open sets and then another 2 open sets, then I'm able to travel from here to there with the same time. So there is synchronization of transfer times. So soon you will see that it's a little bit more than transitivity. And you have mixing, which means that if I take open set, another one, then I will, at some point, I start to intersect, my open set will start to intersect the other one, and they will stay like this forever. They won't be disjoint. Okay, so, and in the order I wrote it, it is how the level of mixing increase. So going down, property which is lower implies the upper property. So mixing implies weak mixing, weak mixing implies total transitivity, and transitivity total transitivity implies transitivity. And of course, you may ask which of these properties you have. For example, in these examples I gave you. So if you look for rotation, because it's rotating, then after very quick look, you see that you have no chance for weak mixing in rotation, because if I take two disjoint intervals on my circle, then that one cannot intersect itself and the other one, so no weak mixing. And with adding machines, you even see that you don't have total transitivity, because some power, if you have these coordinates, and some power will fix one of these coordinates. And that way, you don't have even total transitivity in that system. And rotations are totally transitive. Okay, so this is kind of hierarchy of mixing that people usually try to prove. Usually, this is the hardest to get if you want to make some construction and keep some other properties. Okay. So, of course, during years, people developed lots of techniques that help you to verify these conditions, and also proved some properties which are related. So, for example, that is very nice. So proximal means that if I have 2 points, then when iterating, the trajectories start to get closer and closer for some iterations. And this is kind of classics. It says that if I have weak mixing and I fix any point I want, then I can find in my space dense set such that point from this set is proximal to my chosen x. Okay, so for every point x, there is lots of points that are proximal to it in the whole space. And it is somehow related to distality. So proximal, you have definition there. I told you, you just get closer and closer. And distal means that nothing like this happens. So point is distal. If I take orbit closure of my point and take any other point, so if I now see that they are proximal, then this point in fact was x. Okay, so point is distal if it is not proximal to anything in closure of its orbit. And then you have two definitions. Point distal, which means there is distal point in your space, or distal system, which means that every point is distal. Okay. So if you look at this condition, then you see that if you have one distal point, then you cannot be weakly mixing. Okay, at least in minimal system, because in your space there is lots of points which are proximal, but you cannot be proximal to anything in your orbit closure. So the only possibility to be weakly mixing and distal is that you are a single point space. Okay, and this is kind of classical result, which says that if you have this substitution of constant length, so means I'm substituting the same words of the same length. So like in these two MRs. See, I was sending its symbol to words of the same length. So if it is like in this example, then theorem tells you, wrong direction. Theorem tells you that you are distal, point distal. So there is one point which is distal, and that way you can prove, for example, that you are not weakly mixing. Okay? So if you look at the structure of this special orbit in two Morse, then probably it's not that easy to say what will be dynamics there. But if you have this theorem, you see that you have no chance for weak mixing, for example. Okay, so for sure, there are systems which are minimal and not weakly mixing. So you may ask, okay, so what about these others? And of course, people were thinking about it also for quite long. Okay, before I go further, let me spend 1 minute on this. Okay, so this is another classical construction. I believe this slide comes from Devani book. So what you can do, you can take rotation on the circle, and now what I'm doing, I fix one orbit on this circle for rotation, and then I blow it up and start to inject some intervals. And as long as I keep the sum of these lengths bounded, I can do that. And that way I will construct some other system on the circle. It won't be minimal because I will never come back to this interval because it will go densely but never intersect itself. But then what you can do, you can kick out these interiors. So we will get something on the contour set and it will be minimal. Okay? But what's the difference between this dynamics and that one? So here you have proximal pair, in fact asymptotic pair, because these 2 points will go closer and closer to each other. Okay? And this type of factors, they are called almost one-to-one. So almost one-to-one means that you, on a residual set in your space, you are one-to-one. But maybe in some other points there is bigger pre-image, like here. Okay? So here, lots of points are covering one-to-one, but these 2 points at the boundary of these intervals, they are projected into the same point. Okay, so this is particular example of almost one-to-one extension with these intervals removed. And as you can see, it can, that way you can introduce lots of new flavor into dynamics, because that one was just rotation, everything was rigid. Here you have some different behavior that you didn't have. So usually people are interested in this type of factor maps. Okay. And what I should say that if I start with minimal map and I have this residual set of one-to-one fibers, then automatically I know that this map is minimal too. Okay, so this is kind of technique that you can try to transfer minimality from here to there. You just take care that lots of points are covered one-to-one and they are dense in your space. Okay. Okay, and this is another tool that you may use to prove that you have weak mixing. So here you have definition of equicontinuity means, so equicontinuous system means that the family of these iterates is equicontinuous. And in other words is that if I take my point, I take neighborhood, and I have fixed epsilon. So if this neighborhood is small, then points from the neighborhood will never separate more than epsilon from my point. Okay, so this is equicontinuous. And then a long time ago, it was proved that you can always find maximal equicontinuous factor. Maximal in the sense that if you find another equicontinuous factor, then you have to go through that one. Okay, so I have one special that if I find another one, I can factorize from this maximal one to the other one. Okay, and this is quite nice property. So here it's if and only if. So for minimal system. For minimal systems, if I'm weakly mixing, it equivalently means that my maximal equicontinuous factor is trivial. So this is one of ways of proving weak mixing, one of way of looking at that. So you look at this maximal equicontinuous factor. If it's trivial, you know that you have weak mixing. And it works only for minimal systems. Okay, for if you remove minimality, then your maximal equicontinuous factor have to be trivial, but you don't have opposite implication. But for minimality, it is a way of looking. And I will refer to this later on. Okay. So eventually, people developed some techniques how to prove this weak mixing. And this is one of techniques which now is quite developed, and many people look or know how to produce nice system using this. And the idea is to put some spacers. So as in the case of this substitution, you produce some 0-1 sequences, but then you put some special symbol, which in new terminology people call spacer, and that way you induce some property you want additionally. So here is kind of condition why to do it that way. So if I know that I have point with dense orbit, and if for every neighborhood, if I look for this set of transfer times, so times when my set intersects itself again, and if I can find the two consecutive integers, then I know I have weak mixing. Okay, and this is mechanism which is done here, because here I produce infinite sequence by this rule, but what I'm doing here, I'm writing down one word, one generating word twice, and then with spacer, and it means exactly what I have there, that I will have to move from this open set to that open set. So from this cylinder to this cylinder, I will need n iterations, and from that one to this one, n plus one. So somehow this weak mixing is there. Okay, but as you can see, I'm also showing you years, so this is kind of really, really old results, right? This Chacon, which is again kind of classic example, 65, so how much is that? 50 years. Okay, maybe I won't speak about it. Usually, so there are two possibilities, because sometimes you need some special property, but you don't care that much about about your space, and in some other cases, it's important where your examples live. So if you don't care about the space, then you have these two classical theorems. So first one, it was proved by Jewett and then extended by Krieger to this version which you have here, and then Lechner provided some additional extension. So what it tells you, it's theorem from ergodic theory, but it's very good from the topic of minimality. So what it tells you, okay, so take any ergodic measure of your choice, any ergodic measure, and then you can find minimal system which has only this invariant measure. Okay, so I have isomorphism between measure which lives on my minimal system and that chosen measure, and there is no other on my minimal system. And this is minimal. Okay, and what Lechner says, it says you can even add topological property of mixing and it still works. Okay, so kind of powerful theorems, because I take any measure I want. It's important it's ergodic, and I embed it somehow in some abstract system living in some space with exactly this measure, so probably with some dynamics, and also with these topological properties. But the problem with these theorems is that you don't know what's the space. It just tells you you have it. And people were also interested in some special instances. So, and then you have to work hard, because then you want to keep your space. And here you have two examples. So this is for almost one-to-one extension of odometers, and it was obtained by Williams, the first result of this type. So you can extend odometer by almost one-to-one extension in such a way that you can put as big entropy as you want. Okay, so you can increase entropy, but what you lose this equicontinuous, so you have to have this almost one-to-one. And the other type of this, it's for Chacon, and also some special extensions, and there they can even prove that there is lots of systems with the same entropy, but they are, from point of view of dynamics, they are different. Okay, so this is 80s, 90s. Okay, so I'm showing this just to tell you that there was lots of work depending how people and what questions people were interested. So some were in ergodic theory, some in topological dynamics, and they were intersecting somehow. Okay. No, not that direction. Okay, so what other, so in these two examples I showed you before, the restriction was that I want to have some special factor like this odometer or Chacon, for example. So another question Or another restriction you can put, you can say, okay, so now most of these examples were on connected space, on totally disconnected spaces. So what if I add connected? Okay, and then maybe the most natural to start are some manifolds. So you can ask, okay, well, what about minimality? What minimal system you can see there? So there is this nice theorem of Blochover, Stigen, and Timchatin. So they prove that as long as you are interested in surfaces, then the only two instances that you can find minimal map on them are Klein-Bottle or torus. So torus, it's not surprising, and it was known that you can have example there because you have these rigid rotations. And for Klein-Bottle, this is also old example by Will Perry. And what this guy showed that you cannot have different. Okay, so this is really nice. That these two examples are actually the only possible. I mean, these two spaces are the only possible among surfaces. And dimension free, I think it's open. Nobody provided full characterization. And probably it is also worth mentioning. So on torus, there are these rotations, but there are also other examples, and this is highly non-trivial one. First one of this type, it was obtained by Mary Rees in '81, and what she was able to show is that on torus you can have minimal map but with positive entropy, and this is really, really hard, and this technique is really deep and involved, and very, very hard to understand. And Judy will have talk about it. So I think at least she will tell you a little bit about this paper, Beguin, Crovicher, and Laroux. So they produce like 60 or 70 pages long paper, making some axioms out of this. So they read the paper, they understand what are the crucial ingredients, and then in this paper from 2007, they provided what more or less you should do to succeed with this construction. Okay, but it's very long. There is like 10 conditions, another 10 conditions, and another 10 conditions. And if you check all of them very carefully, then you will get what you want. Okay, so this is this type of paper. And it is generalization of Mary Rees. Okay, so this is for surfaces. Okay. Okay, that probably I don't have to show, but anyway, I will do it very briefly. So in some slides, some next slides, another important examples of connected spaces will appear. So one important for me will be pseudo-arc, which is arc-like hereditary indecomposable continuum, kind of classics for people working in continuum theory. So this is the one. And the other one will be pseudo-circle, which have similar flavor, but still, so it's still on plane, but now it separates the plane. So from point of view of minimality, pseudo-arc is not good because it has fixed point property, so you will never produce their minimal system. But in fact, for pseudo-circle, you can do it. And there is another classical result when it was done. It was done by Michael Handel in '82. And the construction is by so-called Anosov-Katok approximation method. So the idea is that you take sequence of rotations, and here you put some homeomorphism. So you somehow deform your space, rotate and deform back, and you construct a sequence of such approximations which uniformly converge, and then you get something at the end. It is the main idea behind this technique. And for pseudo-circle, by Handel, it was, so the sketch, how this construction was done, he was taking annulus and inside, and with some rotation, periodic rotation, and then in this annulus, he was embedding another more crooked one, which is invariant under this rotation. So it's like on this picture, you have 4 iterations to come back, and you have this curve which is invariant. And then on this curve, he changed this rate of rotation a little bit so that everything is converged, but that way, because changing this rotation, so by this technique of Anosov-Katok, he knows that it will work. I mean, he will get some map at the end. But because of these faster and faster rotations, he at the end is able to get some homeomorphism. In fact, he was interested in smooth dynamics. But you may think he obtained plane homeomorphism such that pseudo-circle is invariant there, and dynamics is minimal on this pseudo-circle. This is important. And there are also 2 more properties. Okay, so in this paper, what he get, minimality, as some byproduct of the construction, he had also this property, which means that for some sequence of iterates, this tends to uniformly to identity. So for some iterates points, every point come back really close to starting position. For some others, something happens, but for some sequence, it's very close to identity. And what he also proved that if you look at rotation number, it is well defined, but you cannot semi-conjugate it with rotation on the circle. Okay, so he also proved it, and he said that the argument he used, he said, comes from Thurston, that it really happens. And at least I don't know any example which is minimal on pseudo-circle and is semi-conjugate to rotation. Okay, so it seems to be open problem. If you can somehow maybe modify this construction or maybe propose another one on pseudo-circle, that somehow you can project it into circle and commute with some irrational rotation. And with Jan and Alex, we are looking at this, and at some point we get to this really simple observation as long as you know how to do it. So we observe that in fact this maximal equicontinuous factor for this map is trivial, so it's weakly mixing. Okay, so this example of Handel is weakly mixing, and for us it was a very big surprise because you do this technique, so you make this rotation, and on the picture I show you, you rotate, so you may think that the structure is so rigid that points never get close together if you start in different sectors. But I show you that result of Aikin and Koliada, which says that there is lots of proximal pairs. And by intuition, it seems impossible, but in fact, it happens there. So for a long time, we were believing there is no proximal pairs at all, but they are. And the space is responsible for that. Okay, maybe I can skip this part. Okay, so now I move a little bit to one question. So question seems not related very much to minimality, but the answer will be related, or some answer to some question will be related. Okay, so this is question that I personally like very much, very, very hard question. It was published, I believe, in Topology Proceedings, in paper by Wayne Lewis, because he collected questions from participants of spring or summer topology, I'm not sure which conference, and then he produced a list of questions. So this type of paper, and the question of Marcy Barch is the following: that if I give you some real number, can you provide me with homeomorphism of pseudo arc with entropy exactly this, which is exactly this number? And it's still open. What you can prove that you can have entropy 0. So this is Henderson example, and you can have infinity, and it follows from Piotr Mintz and Trencio paper. So these examples of 0 and infinity are known, and both are through inverse limit. And then not so long ago, Chris Moron proved that, in fact, through inverse limit, you cannot get different numbers. So maybe these are only possible, but we believe that it's possible to get something else. But with Jan and some other people, we were talking a lot and trying to prove it, but so far we don't know how to do it. So this is still open. And as I said, the only examples have 0 and infinity, and on some other hereditary indecomposable continua, there are also examples of this type, like pseudocircle. That one I showed you, this minimal one, it has entropy 0. Again, infinity we can also get. So probably this led Chris to state this question. So maybe he asked, okay, maybe that's the case for every hereditary decomposable continuum, that you can get only 0 or infinity, because somehow examples were confirmed this statement. And what we were able to prove with Jan and Alex is that at least for this more general question, so although we don't know what happens on pseudo-arc, we know that for sure there is some hereditary in the composable continuum, that you can have positive non-infinite entropy. But the space is a little bit complex. I will show you in a moment how you can think about this place. So somehow we produce hereditary in the composable continuum and some homeomorphism on that space that it has your given alpha as entropy. And as byproduct, so as I said, maybe the question is not about minimality, but as byproduct of this technique, we have minimal and weak mixing. So it seems that maybe for this positive entropy, minimality is somehow important. We don't know, but at least for our technique, it's like that. Okay, so instead of giving you exact description how this technique works, I will just sketch you how it works. Okay, so here, imagine this is this example of minimal map on pseudocircle embedded in annulus. So you take lift of this map. So I have now strip. I have my map living there. Okay, so I lift my map. And then maybe this is better. And now I multiply it with I take product with some space. In first instance, let it be Cantor set. Okay, so I take this strip, multiply by Cantor set. So this is Cantor set of these strips. And on my Cantor set, I select some minimal map. And then I introduce relation, which is like in the case of suspension. So these 2 points here, they are related. With integer distance, they are related if one is image of other one by my chosen homeomorphism of Cantor set. So it's like in suspensions, but now it's much more complicated space. So somehow I glue this space back, but now I glue it on different levels. So you can imagine this like I have different levels of this annulus winding somehow around and around using the structure of my Cantor set and my map. Okay, so when I show you in a moment, if you don't know what are suspensions, then the next slide maybe it will be more clear. And how we get it into this manifold, because we can find this minimal Cantor system in plane, like starting from Smale horseshoe, for example, and that way it is why in this theorem, which we have, if we want this example to live in nice space, it is why we need 4 dimensions, because we need 2 to have my homeomorphism Cantor set living somewhere, and then 2 another dimensions come from this annulus. Okay? But anyway, so this is kind of general technique. So we can really get different spaces. Okay, so just to give you some intuition, if you haven't seen how these suspensions look like. So you just take your point, you move along some line, and then you wind it and glue with h of x and so on and so on. So that way you get it. And for example, is the way how you can produce solenoid or some other continua. So yeah, and in the case of this result I show you, so the flavor is similar, but now I don't have lines which I wind around, but I have kind of complex thing like the whole space somehow winding around using this map, which tells me which I should glue with what. So it's really hard to imagine how these spaces look like. Okay. Okay, so now I'm moving to another questions that we were interested, and they were around for some time. So another group of questions that people were interested in were what about minimal maps and non-invertible minimal maps? Because that first examples, they were homeomorphic, like rotation. So what if you say, okay, now I want my map additionally for sure not to be homeomorphic. So on circle you cannot do it. So there were questions, okay, what about other spaces? So on circle, very soon by some other results, it was possible to say that on circle you won't find map which is, I mean, if you are minimal, you have to be homeomorphic. But on some other spaces like torus or solenoid, you can construct such examples. On plain bottle, you also can do it. Okay, and as byproduct of work on some other question, I will show you in a moment, again with Alex and Jan, we were able to show that this suspension, if I start with suspension on maybe Cantor set or maybe something more complicated, then I always can, the space I will get as a result of this construction, I always can find their minimal non-invertible map, as long as my map, which I used to gluing these points, it was minimal at start. So Cantor set is good, but also some other spaces are good, and that way we are able to produce lots of, so for example, these two things like solenoids, we get it for free. For torus, we get it for free. For some other continua, we also get it for free. Okay, but the main question we were working was from Bruin, Koliada, and Snocha paper. It will appear in the next slide, but just tell me about some other questions which were related to that one, and non-invertibility. Yeah, so yeah, there should be yes there. Okay, so the question was, okay, because for the circle the situation was okay, I have homeomorphism which is minimal, but no map which is non-invertible and minimal. So the question was, what about opposite? Can I have space that there is minimal map, but no homeomorphism which is minimal? And this was done by Koliada, Bruin, and Snocha. Yeah, and right. And another question was that if circle is unique space, one-dimensional space with the property that you have homeomorphism, which is minimal, but no other map, and they also were able to produce example. And this example is nice and is related for work with Jan. Okay, so very brief explanation, what is the space and what they did. Okay, so just in case, so the authors are Dovnarovic, Snocha, and Tivoniuk. I have there, okay, Dovnarovic, Snocha, and Tivoniuk. So what they did, they started with solenoid. Okay, so they take this suspension of odometer, they start with solenoid, and then what they do, they choose one composant in the solenoid. There is point with dense orbit living there, and they do similar thing to Don Juan, but instead of putting intervals, they put this sine 1 over x curve. Okay, so in one composant, they start putting this curve. Okay, so just to. Okay, so this is solenoid. Here is your minimal map, and on this composant, point is moving by this number which you use for rotation, so some t is moving, and I blow it up and put here sine 1 over x, okay, by some technique. But what additionally they do is that after this procedure, the map is minimal again. Okay, so they do this procedure, somehow extend the map, because now instead of points I have some strange continuum, and they prove that you have minimal map there. And because of this procedure, they then prove that actually any homeomorphism have to be translation of these inserted objects. So that way they prove that if they look into homeomorphism group, then in fact it's cyclic and it's generated by this one original map they started with. Okay? But they also prove, so by the construction, they have this minimal homeomorphism, but then they also prove that if you are not invertible, then in some sense you have to map one of these intervals into inside, and then you will produce fixed point. Okay, and this is how this example, the main idea about this example. So they put some obstacles which are sine 1 over x, and then they prove working hard that it's what they need. Okay, and there is the question from this Bruin-Koliada-Snocha paper, which asks, okay, so now imagine I have space where I have minimal map and I have another, take Cartesian product. Will be there minimal map as well? This was the question. And maybe the most natural is to look x and y the same. And you see if you look on Cantor set, product is Cantor set again. So the answer would be yes. Looking for this example for circle, again, circle, and on torus you have minimal map, so that's okay. So you may think the answer is that this minimality survive, I know. But actually the answer is no. So it is the result we have with Jan and Alex. So we were able to produce almost one-to-one extension. You may think of solenoid, maybe to make it simple. But now, in this one, it's very similar structure to what have these guys putting sine 1 over x curve. But now what we pack into these fibers are pseudo-arcs. Okay, so we developed technique how to, into solenoid, blow up and put pseudo-arcs instead of these points, keeping map minimal. And then it's mainly responsible for what we have. Because of this special structure, we are able to prove that the answer for this original question is no. So you can find, in fact, continuum with minimal homeomorphism such that if you take product with itself, you won't find their minimal homeomorphism. Okay, so this answered this question for 2003. And just to finish, so after we show up this example, Snocha and Spitalski, using similar argument, they proved that in fact in this original Slovak space that I showed you before, you can prove that in fact there is no minimal, in the product there is no minimal map at all, so invertible or non-invertible. And this is question we think is interesting, but so far we have no idea how even to attack it, because this technique we use, it won't work. So it would be nice to have a space that this minimality breaks, but after some iterates. So like maybe take y product with itself, it has minimal homeomorphism, but maybe 3 times is the point where you cannot find it. but we don't know, and for sure the technique we use don't lead to the answer, or at least we don't know how to do it. And I should stop here. Thank you very much.
I think we have about 2 minutes for questions, and there's a request that if you would like to ask a question, then there's a microphone, and please speak to the microphone, okay? So, any questions? All right, well, if there are no questions, let's thank our speaker again.